Good morning, everyone. Myself, Priyadharshini, working as assistant professor in the EEE Department of R&D Engineering College. Today, we are going to see a topic from the subject digital signal processing, and especially the topic is around the IAR filters, how to design the IAR filters. So, we will move to the topic. So design of IIR filters, infinite impulse response filter. So first, in order to design the filter, design it in the analog pattern and then it has to be converted into the digital specifications. So here, the frequency response of the ideal and the practical analog filters they have represented. So this is going to for the low pass filter, high pass filter, and band pass filter and band stop filter. So how they have to be, that is practically it has been represented with this the low pass filter. So what is your magnitude, and here is the pass band and the stop band allowable errors. So they are represented, and they are cutoff frequency, pass band frequency, and the stop band frequency. So this is for the low pass filter and high pass filter, band pass and band stop filter. And design of the digital filters from the analog filter. So we have to design the digital filter. So map the desired digital filter specification into those for an equivalent analog filter. So derive the analog transfer function first and an analog prototype, and then it has to be converted into the digital format. The specification and the magnitude, that is the response of the low pass filter they have given. So here it is h of j omega, so pass band and its stop band, and here it has been for the digital low pass filter. And what are the specifications? So it is going to be the pass band frequency, and this is the stop band frequency and cutoff frequency. The parameters allowable pass band. This is the parameter specifying the allowable stop band, analog frequency representation, and this is going to be the digital frequency representation, pass band error, and allowable magnitude in the stop. Design of a Butterworth filter. How to design a Butterworth filter? Okay, so this is of IR filter. So step one. So from the given specification, so first you have to find the order of the filter again. So n has to be, that is greater than or equal to log of root of 10 to the power of 0.1 alpha s minus 1 by uh, 10 to the power of 0.1 alpha p minus 1. So omega log of omega s by omega p, or otherwise it can be said as log of lambda by epsilon on the log of omega s by omega p. By this we can get the order of the filter, and then we have to round off the order of the filter for the higher integer, and then you find out the normalized transfer function. And for the Butterworth filter, if the order of the filter is like this, what should be the denominator? If it's 1, it is going to be s plus 1. If it is 2, s square plus root of 2s plus 1. And similarly, 3 means s plus 1, s square plus s plus 1. So like this. And from then we have to calculate the cutoff frequency by using this formula and find the transfer function. To find the transfer function means this is a normal transfer function, and then at the s, that is for the high pass filter, means the cutoff frequency has to be, that s has to be transferred into cutoff frequency by s. If it is of a low pass filter, it has to be transferred like s means s by omega c. And the next is going to be the steps to design an analog Chebyshev filter. This is another type of the filter. Okay, one more type, the next type of the low pass filter. For the given specifications, again, the order of the filter can be calculated by using this formula: cos h inverse of lambda by epsilon by cos h inverse of stop band and pass band frequency. And similarly, here also we have to round off to the next higher integer and find out the parameters of k, mu, and epsilon, A and B, and pass band frequency and allowable attenuation band. And steps 4 is to calculate the poles for the Chebyshev filter and the denominator polynomial for the transfer function. And the step 6 is the numerator of the transfer function depends on the value n. So we have to find out if it's of an r, the value has to be substituted as 0, and if it is of an even, has to be 0 in the denominator polynomial, and divide the result by root of 1 plus epsilon square. So then they are comparing between Butterworth and Chebyshev filter. Butterworth filter's magnitude response decreases monotonically, and Chebyshev exhibits ripples. Transition band is more and the transition band is less. The poles of the Butterworth filter lies on a circle. It lies on an ellipse. For the same specifications, the number of poles are more. For the number of poles or less, on the order of the Chebyshev filter is less. Okay, so bilinear transformation. So we need the transformation to in order to convert from the analog to the digital filter. So first we are doing the bilinear transformation. So a wrapping effect. So what is the wrapping effect? The omega, and this omega represents the analog to the digital frequency, and omega is equal to 2 by t tan of omega by 2. Okay. So here it has been transformed like this. So pre-warping is the warping effect can be eliminated by pre-warping the analog filter. This can be done by finding the pre-warping analog frequency using the formula 2 by t tan of omega by 2. Design procedure for bilinear transformation. Okay, step 1. From the given specifications, find the pre-warping analog frequencies by using the formula 2 pi t tan of omega by 2. Use the analog frequency h of s of the analog filter. Select the sampling rate and substitute s is equal to 2 by t 1 minus z inverse by 1 plus z inverse into the transformation of the steps 2. Design of the IAR filter using impulse invariance method. So this is another method in order to convert analog into digital specification. For a given specification, find HA of S. Select the sampling rate for the digital filter, and similarly HA of S can be transferred, that is represented with the function summation k tends to 1 to n ck by s minus pk, that is the poles, and compute the Z transform of the digital filter by using this formula. So we are moving to a problem. Design a digital Butterworth filter satisfying the constraints 0.707 less than or greater than or equal to h of e power j omega greater than or equal to 1 for 0 less than or equal to omega to pi by 2. Okay. But the t is equal once again using bilinear transformation as well as by using the impulse invariant technique. From the specification, we are finding out what's the lambda value and the epsilon value. So lambda value is 4.89 and the passband frequency level is going to be 3 pi by 4. So step 1 is find the order of the filter. If I'm finding the order of the filter, it's around 3.9. So round off to the nearest number is 4. So if it is of the 4, the denominator is s square plus 0.76537s plus 1, and similarly this. And substituting the value of h of s, and omega c is equal to omega p by epsilon 1 by n, and the value is 1.57. So h of value is s tends to s by 1.57. If I'm substituting that value, and after the simplification, this is our technique, and by using impulse invariant method, we are finding out the poles for that. So that is, we are taking the conjugate of that, and we are calculating a conjugate and b conjugate and substituting in that. And finally, the h of z. So t is equal to 1 second, right? So h of z is, we are converting that into the transfer function. The final answer is 0.725 plus j 1.754 1 minus e power minus 0.6 j 1.45, and similarly a conjugate and b conjugate. So like this, by using the impulse invariant technique, we are converting an analog into the digital filter. And by using the bilinear transformation, so we are calculating the passband frequencies pi by 2 and 3 pi by 4. And by using this pre-warping effect, we are calculating the corresponding frequency 2 radians and 4.828 radian seconds, and calculating the order of the filter. And it's going to be the 2. And by if it is 2, this is our denominator. And then we substitute the value, and this is our final h of s. By using the bilinear transformation, we know that s tends to 2 by t 1 minus z inverse by 1 plus t z inverse. So s has been transferred into the corresponding z transform, and we are getting the h of z. After realizing the h of z, the design of the filter can be obtained. Okay, so like this, we can able to design an analog filter, uh, that is digital filter. First, we are designing that in the form of an analog, and then we are converting that to the digital filter by using the different transformation. One is a bilinear, another one is a impulse invariant technique. Thank you.